Bhandari sir, good evening.
Hello, Dr.
Hello.
Joseph.
Yeah. Very good evening, Saubandhu sir.
Yeah. Very good evening.
Good evening, Sabandhu sir.
Good evening, Dr. Sin.
Good evening, Saubandhu sir.
Bhandari sir, good evening.
Good evening.
Bhandari sir, good evening. Yeah. Sir, you are muted, sir.
Good evening to you all.
Good evening. I think Anil, you are in USA, I suppose.
Yeah. I am in Los Angeles. Yeah.
Yeah. I was told.
Early good morning to Anil, Dr. Anil.
Yeah. Thank you, Dr. AP.
Excuse me, I will on my laptop also because sometimes we might not get power regularly, continuously.
Okay, sir.
Good evening, Anu.
Good evening, everyone. Good evening, Joseph sir, Singh
Good
sir,
evening. Good evening.
Bhandari sir, namaste.
Namaskar.
Sabandhu sir, good evening to you.
Good evening, everybody. I'm
Good
Sir,
Prasad.
good evening.
I think we have to provide the screen sharing facility to the resource people, no?
Should we start or wait for some time?
Madhav sir, very good evening. Madhav sir. Sir, you are muted, sir. I think we can start. Sabandhu sir, shall we start?
Okay.
Okay, Dr. Anil.
Yeah.
I will share my screen. Is my screen visible?
Yes.
Very good evening to all the participants, eminent participants, and early good morning to Dr. Anil. Today is a very important day for the mutual relationship between two geotechnical societies, that is Indian Geotechnical Society and Sri Lankan Geotechnical Society. Both the societies are going to start officially technical knowledge sharing exchange program via this joint webinar series on geohazard. I would like to highlight the background for the proposed activity, this activity. So I will brief about what happened in the background so that we are able to start this program. During first Geo Mandu 2023 at Kathmandu, Nepal, South Asian Geotechnical Societies came together to collaborate and enhance geotechnical advancement in the region. So, and a society for South Asian Geotechnical Societies were formed. So during IGC, after that, during IGC 2023 at Roorkee, Indian Geotechnical Society had a MOU, signed an MOU with Nepal Geotechnical Society, NGS, and Sri Lankan Geotechnical Society. After that, the Nepal Geotechnical Society, NGS, and Indian Geotechnical Society have already successfully organized the first Indo-Nepal webinar series on 6th of April 2024. After that, all the pictures are here. After that, the Indian Geotechnical Society and Sri Lankan Geotechnical Societies are teaming up for a special webinar in Indo-Sri Lanka webinar for geohazard. This webinar series is to exchange knowledge, experience, and expertise between the members of both the societies. This will enhance geotechnical practices and promote excellence in the field of geotechnical engineering and landslide hazard management. This joint effort will not only strengthen bond between the two countries, between the two societies, but it will also foster better relationship between the two nations. Objective of this webinar series is to exchange knowledge, experience, and expertise between the members of both the societies. This webinar series will especially focus on geotechnical engineering and geohazard topics, which includes rainfall-induced landslide, debris flow, coastal erosion, port and offshore structures, rock/soil slopes susceptible to cut slope failures. So with these objectives, we have started this program and this webinar series. And today we are taking the rainfall-induced landslide, which is the first theme of this webinar series. So two speakers we have chosen. Both the two speakers are prominent experts in their country and in their society. So now I will call upon Dr. Sahabandhu, SLGS President, to give the brief introduction about the Sri Lankan Geotechnical Society. So now, Sahabandhu, sir.
Thank you. Thank you for the invitation, Mr. Singh. Dr. Anil Joseph, the President of the Indian Geotechnical Society, Dr. Mandip Subedi, President of the Nepal Geotechnical Society, distinguished guests at national and international levels, past presidents, and members of the executive committees of both the Sri Lankan and Indian Geotechnical Societies, members of the organizing committee, members of both the Sri Lankan and Indian societies, and ladies and gentlemen. As the president of the Sri Lankan Geotechnical Society, I am delighted to welcome you to the first webinar of Indo Sri Lanka webinar series on geohazards. This initiative, a collaboration between the Indian Geotechnical Society and the Sri Lankan Geotechnical Society, aims to facilitate the exchange of knowledge, experience, and expertise among members of both societies and the international community of geotechnical engineers. Our focus on critical topics on geotechnical engineering and geohazards. The webinar series will cover various topics, including rainfall-induced landslides, debris flow, rock and soil slopes, susceptibility to failure, coastal erosion, and port and offshore structures. We are honored to welcome you to the inaugural session, which features two distinguished speakers. My friend, Professor Atula Kulatilaka, Emeritus Professor at the University of Moratuwa, Sri Lanka, will present on rain-induced slope failures and rectification techniques, sharing his extensive experience through several case studies on slope stabilization, including drainage systems and slope reinforcement. Professor Nilima Satyama, the professor of IIT Indo, India, will discuss rainfall-induced landslides, monitoring and mitigation measures, drawing from her research in geotechnical earthquake engineering and landslide hazards, particularly focusing on tools for early warning and disaster risk reduction in vulnerable regions. The webinar series will strengthen the collaboration between the Indian and Sri Lankan Geotechnical Societies, fostering improved working relationships and encouraging neighboring countries to form a South Asian Geotechnical Society in an effective manner. Such an organization would significantly contribute to the development of geotechnical engineering in the region. I would like to extend my gratitude to our distinguished speakers, Professor Atula Kulatilaka and Professor Nilima Satyam, for accepting our invitation to be the resource person for this event. I also thank all members of the organizing committees in both India and Sri Lanka for their tireless efforts in making this event possible. Additionally, I extend my thanks to all participants, as your involvement is crucial to the success of this event. I am deeply appreciative to the support from the members of the Sri Lankan Geotechnical Society Executive Committee who have worked with me to ensure the success of this event. I would also like to thank Dr. Mark Polos, President of the ISMG, and Professor Albert Shaw, Vice President of ISMG Asia, for their encouragement for such events. Furthermore, I thank the key bearers of the South Asian Geotechnical Association for their support. This year, our society has organized GeoForum, a monthly short presentation event followed by question and answer sessions, and an annual seminar to enhance the knowledge of engineers and professionals in geotechnical and foundation engineering. We are also planning our international conference in 2026 in Colombo. I cordially invite all of you to participate in these events to support the Sri Lankan Geotechnical Society in its continuous effort to advance knowledge in geotechnical and foundation engineering. Thank you very much.
Now it's my pleasure to invite Dr. Anil Joseph to give an introduction about the and programs of Indian Geotechnical Society. Dr. Anil.
Yeah, very good evening, all of you. It's a proud privilege for me to be part of this webinar series, a dream which is coming true, where we started the journey with the formation of the South Asian Association of Geotechnical Society. And I would like to welcome our President of Sri Lankan Geotechnical Society, Sri Sagabandhu Saab, and President of the Nepal Geotechnical Society, Mandip Subedi, and all the other distinguished delegates who have come up for this meeting, including the people of the day, the speakers Neelima Satyam and Professor Atullah Kolatangar. And also, I would like to acknowledge the presence of two Indian geo legends who have contributed the relationship for the development of relationship between India and Sri Lanka. We have with us today our Ajayendra Kumar Bandari sir and Madhav sir, who has contributed a lot for the relationship. So these recent events happened with the formation of the first Geotech, first Asian Society, Association of South Asian Society, which happened in Kathmandu, like our secretary AP Singh pointed out, and we had made those MOUs, and soon we are going to have a tie-up with Pakistan and as well as Bangladesh to improve the relationship in this area. And thank you very much for all the organizing committee members for taking the effort. And also I would like to welcome all the members from both the societies who is actively taking part in this program. Let me share the screen to talk a bit about the Indian Geotechnical Society. Yeah, is my screen visible?
Yes, sir.
Yes, sir.
Yeah, let me take a brief about in another 2 minutes about the Indian Geotechnical Society. And talking about a bit about India, the 7th largest country by population and by area and the most populous country. India is the land of harmony in diversity, and India is the 5th largest economy currently and the 3rd largest on the average annual GDP growth rate of 5.8%, and the purchasing power the 3rd largest country. And it was coming to the society was established way back in 1948, and it's affiliated to the International Society of Soil Mechanics and Geotechnical Engineering. And we also have a journal published by Springer called IGS Journal, and we have annual conference since '83. We have 55 chapters with 6,500 members spread across the country. So we also have this journal and the newsletter. And also now we have a very vibrant website and online membership, student membership, and e-learning resources, journal quality, etc. also comes up. And this is for the students of the Nepal for the Sri Lankan Geotechnical Society also. And we have a software, we have this license for plastics 2D and 3D. And if you can get registered with the Indian Geotechnical Society students membership, we are discussing among ourselves, we want to open it up for the students of Nepal as well as Sri Lanka to make use of this software licensing which is available, but I have to get the approval of the committee. But this was something which I discussed with Mandeep and team when I was in Nepal after the interaction with the students. But definitely I know from the Indian Executive Committee will give the permission to do that, and together we can able to promote young engineers. And I always say that is the most vital aspect of our relationship. And this sort of webinar where we are talking about the most critical element, the safety and the life-threatening aspects which happen, especially during landslides in our countries, especially Sri Lanka, Nepal, and India. So we have to work together, collaborate, and come up with solutions so that it will be helpful for each other. So this is the concept with 1,500 Indian rupee for the student membership. We will try to come up with a special package for Nepal as well as Sri Lankan Geotechnical Society. And talking about IGS is quite active. I don't want to get into that, but I would like to come up with 3 new things which is coming up. We need the IGS 2024 is coming up to 19 to 21 December 2024 at Aurangabad. Thanks to Manish Dishit and team, they have more than 800 abstracts right now, and it is will be a memorable event which is going to happen in Aurangabad. And this is the important dates. And now we have the first Geotech Asia, which I will be talking towards the end of the program, but to welcome all of you for that. But this is the major event, and thanks again to Nepal and Sri Lankan Geotechnical Society to make it happen, because when we were first bidding for Asian Young Geotechnical Engineering Conference after Geo Kathmandu, India received only 3 votes. Now, out of the 21 people voted, we have getting 18 votes. That means our networking has playing well, and the relationship with our brothers in the neighborhood is making a significant impact in the Asian Geotechnical Society. And soon we want to show our strength across the international society that we together are capable of being the leaders of the international society. So I will come to the first Geotech Asia invitation. And also I would like to congratulate Professor Neelima, the resource person today, for she is taking a lot of effort to have the 12th international conference on field instrumentation and monitoring, which is scheduled to happen 12th ISFMG 2026 in 6 to 10 August 2026. So these are some of the brief about that. And of course, this collaboration is now quite working well. We have tie-up with Sri Lanka, Nepal, USA, Brazil, Japanese and Korean Geotechnical Society. And thank you very much for the patient listening. And as a geotechnical engineer, I feel it is very important that we share our knowledge, work together, move forward together and bring a lot of impact. And also I would like to acknowledge the presence of the National Executive Committee members of both Sri Lankan and Indian Geotechnical Society who have joined the conference, and I know who joined this webinar. And sorry for the slip of my tongue because it was too early in the morning and just I got up from the bed after a hectic flight of 27 hours from Nepal, Kathmandu, to participate in the program in Los Angeles. And just now in the morning I got up, so sorry for that, and wish all the very best for this webinar. And thanks the resource persons once again and the eminent personalities who have joined us for this program. Thank you very much, and over to you, AP.
Thank you, Dr. Anil. We can understand your problem because since last 45 days, you have not gone to your home even for a single day. So we can think of how much efforts you are putting for the growth of our geotechnical society. And now our very eagerly waited lecture is to be started. So first, I would like to take the privilege of introducing our first speaker, Dr. Professor Athula Kulati Laka. Is my pronunciation correct, sir?
Yes.
I think Kulatilaka.
Kulatilaka.
Good to see you, Atula.
Yeah. Nice to see you, Professor Madhav.
I'm in Dallas, so from there, like Anil, we are both in US. Okay.
Right. You are away from the India.
Yeah.
Professor Kulati Laka is a well-known expert in geotechnical engineering, and it's a mere formality to introduce him here. He is an emeritus professor at the University of Moratuwa, Sri Lanka, has extensive expertise in earth-retaining structures, ground improvement technique, and slope stabilization. He has advised the RDA on geotechnical engineering for expressway construction, focusing on soft ground improvement and cut slope stabilization. As a consultant to NBRO, he has contributed to numerous landslide rectification projects. Additionally, he is the past president of Sri Lankan Geotechnical Society. He has mentored many young engineers in the field. With this very brief introduction, I know everybody knows you very well. I would invite Professor to deliver your lecture and give us the knowledge about that.
Right. I hope you can see my screen.
Yes, sir.
Right. Good evening. Thank you very much. And I'm very happy to contribute to this India-Sri Lanka joint effort in enhancing the knowledge in geotechnical engineering. And I'm very happy to note the presence of Professor Madhira Madhav, a very long time friend of mine and in Sri Lanka. And also I noted that Dr. R.K. Bandari was there, who had been in Sri Lanka, contributing to the improvement of geotechnical engineering in the country. We have worked close together, a long time friend of Sri Lanka. So it's a great pleasure to see both of them in the audience. So with that, I will start my presentation. So over the next 45 minutes or so, I will talk about the efforts taken by us in the reduction of risk of rain-induced landslides in the country. So this is the map of Sri Lanka with all the geographical details. We have an extensive, we have the central highlands of the country, which is critical, surrounded by an extensive lowland area. The annual rainfall comes from two major monsoons. Southwest in May to September and northeast from December to February. The rainfall quantities are given here in the slide. So the population is well distributed throughout the country. So as a result, there's a well-connected road and rail network. And this road and rail network needs improvements quite often. And also there are infrastructure improvements to be done. With that, there are a lot of landslides that are taking place. Sri Lankan geotechnical engineers face the challenge of maintaining these slopes stable in this picturesque landscape. Sri Lanka falls in the region that is more susceptible to landslides, as you can see from this map. Now, this is the central part of Sri Lanka, Central Highlands, the elevation ranges, elevation map. This is the slope map. So these two correlate very closely with the map of landslide events, as you see here. And also it correlates with the landslide hazard zonation mapping done by Sri Lanka NBRO. So here is the rainfall map, the rainfall variation. So that again correlates closely with the landslide events. Talking about the background geology of Sri Lanka, sloping grounds in Sri Lanka are formed of rocks of different levels of weathering, residual soils, and colloidal soils. Rocks are mainly metamorphic. Principal rock types are gneisses, charnokites, marble, and quartzites. And these rocks have banded structures with one or more joint planes. These joint planes will remain as relic joints in the weathered product, the residual soil. The mineralogical changes in the metamorphic rock and weathering under the tropical conditions have resulted in layers of contrasting strength and permeability. As you can see here, these charnokitic rocks remain unweathered at this moment, while the gneissic rocks have weathered to form this lateritic soil. And here you have charnokitic rocks, budines, in a matrix of residual matrix of the residual soils. So also next one, you see here the feldspar-rich gneisses have weathered to form this clay-rich soil, which is highly vulnerable and of low shear strength. Charnokitic budine structures are here in a matrix of lateritic soils. So you get that kind of high variations in Sri Lankan slopes. You can witness that only through a cut slope. Now, many of these slopes are with low water table. Many of these slopes are with very low water table during the periods of dry weather. So the prevailing matrix action makes them stable. And we can make near vertical cuts to even 10 meters or more during the dry period. But infiltration of rainwater, loss of matrix function, and perhaps development of perch water table conditions make the slopes unstable. Now, most of the landslides occur in the boundary between colluvial layer or residual soil, or the residual soil layer, residual soil and weathered rock boundaries, or sometimes within the colluvial layer itself. In the modeling of rainfall infiltration, two most important characteristics needed are the soil water characteristic curve and the hydraulic conductivity function. We have obtained these parameters for many different soil types in the country using different experimental processes using method of continuous measurement, pressure plate apparatus, or WP4C dew point potentiometer, and also using various empirical relationships based on particles as distribution developed by Fedden and Singh, Zapata, and so forth. So some of the curves are illustrated here. With this data, we have modeled infiltration into different slopes and the effect of that on the stability. Here, one of the very early studies modeling the infiltration into a cut slope in Sri Lanka. Case 1, the cut slope is made completely of residual soils. Case 2, there is a weathered rock underlying the residual soil. So initially, there is a metric suction of 100 above the water table. It is the variation. With continuous infiltration, metric suction is lost to a depth of about 5 meters at the section 1 with a moderate rise of the groundwater table. In the lower part in the section 2, the metric suction loss is effective for a greater depth at a higher groundwater table rise, high groundwater table rise, and with a greater intensity rainfall, not only the suction is lost, but there are positive pore water pressures, which is referred to as perch water table situation, and a greater rise of the groundwater table at section 1, and destruction is greater in section 2. When there is a layer of lower permeability, weathered rock present below the residual soil layer, so the penetration of water into that is inhibited, and as a result, at the boundary, you will get this kind of pore pressure built up. So with this process of infiltration, the shear strength will decrease and the safety margins will decrease, as illustrated in here. Under different geological conditions and different rainfall intensities, the net result is, with the prolonged rainfall, the factor of safety of the slope will decrease. So with that, the potential failure surfaces can be shallow in most cases. So this is a pictorial illustration of what I showed there. So this near vertical cut slope was done without any geotechnical input. No drainage measures were done. So it lasted only 2 months, only for the very first rain that it experienced. You can see the sliding that have taken place in this slope with the very first rain that it experienced. This is again another example that I quote always. So this is a 1-to-1 degree cut slope done in the Southern Expressway. The work was sort of stopped for some time due to some contractual dispute. So there were some colluvial soils up here you can see, and you can see the drainage parts, and here you can see the water percolating in an uncontrolled manner. So this was going on like that for about a year or two, and so this is the end result. So it ended up as started as a slide, ended up as a flow, and you can see all the soil right up to the bedrock has moved down. So these are some examples of landslides that have occurred in the road network of Sri Lanka. And these are some other landslides that have occurred in general sloping grounds of Sri Lanka. You can witness the destruction that it has caused. With this, you can see that all these failures marked on these particular days have happened after a period of prolonged rainfall. Now, with the very high intensity rainfalls that we receive with this climate change effect, situation is a little bit more complicated. What have we done to reduce the risk of landslides? We have worked on 3 different fronts, I would say. Risk identification, the risk levels are identified through landslide hazard simulation maps, and on specific sites, we do specific investigations to design remedial measures. Then there is risk communication through monitoring. The rainfall is the main factor that is monitored. We monitor the subsoil variation as well in specific sites. So early warnings are issued to people based on the monitoring data, which I will elaborate in a little while. Then there are education and awareness. People in the critical regions are educated about the early signs of the landslides and what to do in such situations. And so they were educated as how to live with these landslides, and they were prepared to face the risk. And then development control, in any new development project, there are stringent conditions that they have to adhere in these sites to make sure that they will not increase the risk. There is land use planning, advice on resilient construction, and specific the slopes that are identified to be vulnerable. Investigations were done and countermeasures were designed. And people from the high-risk areas were resettled in the areas with no risk or low risk. The National Building Research Organization is the major government body designated to handle this risk of landslides. They design and implement risk management measures. This shows the landslide hazard zonation mapping, which started with UNDP assistance in 1990. Dr. Bandari was part of this project. So 1 to 50,000 maps were produced for all these critical areas under that. And thereafter, they are refined to make 1 to 10,000 maps at present. Most of the work is completed. So this mapping was done taking into account 6 terrain factors as listed here: bedrock geology, soil types of soils, the drainage and hydrology, landforms, and so forth. So these were the scores assigned to each terrain factor. So based on the site conditions, which was done by mostly by field visits and looking field visits into the sites, the different values were assigned for these parameters. So they were added up to get the final score. Depending on the final score, you will get it is categorized into either land ice are to be expected, modest level, or low level, or say slopes. This illustrates the process for 2 particular locations, how these different parameters were assigned scores, and the final score based on that, how a zonation was assigned to a particular area. These zonation maps are used by developers and various government organizations in their decision-making process of the development projects. Now, these maps have successfully predicted the initiation areas of some of the major landslides. You can see with Aranayaka landslide and the Nayagama and Asangulu landslide, the initiation areas were well predicted, but the debris, this is the initial area, so debris flowed down to flatter ground. So this hazard zonation mapping does not account for the debris flow area. So that is also very important because these are highly populated areas, and deposition of these debris can or has caused many fatalities. So at present, we are involved in developing the runout areas to estimate the total flow area affected by that. So it can be done with 2 approaches: empirical approaches. So we are now using, with the JICA assistance, the yellow and red zone thing under this approach. And also there are analytical approaches, numerical methods, closely formed equations, and so forth. So we are working with this LS rapid program now, making the data, getting the data from Ringshey apparatus. So this is a mechanistic model, getting the data from the Ringshey apparatus to get the runout areas, the total area that would be under threat as a result of the landslide. So that is also important. That is also very important in addition to the initiation area. For the purpose of monitoring, we have a large number of automatic rain gauge stations stationed in the critical parts of the country. So the data from these stations come to the National Building Research Organization, the major government body. Then in collaboration with the Disaster Mitigation Center, people in the area were warned, the appropriate warnings were issued to the people in the area. Now, at present, these rainfall threshold values for these warnings are based on empirical findings. If the rainfall is about 75 millimeter and continuing, we ask them to be on the watch out. If it is exceeding 100 millimeter, they were alerted. Then if it is exceeding 150 millimeter or 75 millimeter within 1 hour and continuing, they were asked to evacuate to safer positions. So all these things are well coordinated. Currently, we are doing infiltration studies on various slopes to find out site-specific threshold values, which are more reliable than a general value. So that needs that infiltration study with all the data. Now, in addition to the rainfall, we are monitoring the effect of the rainfall on the subsoil at number of identified critical sites. Practically, it is difficult to do it everywhere in the sloping grounds. So we are monitoring the moisture content changes, matrix suction loss, and the pore pressure development, and the effect of that, the ground movements at the surface level and the deeper levels using appropriate instruments. We have the moisture sensors, tensometers and piezometers, water level meters to measure the changes in the pore pressure regime, then extensometers to measure, and the tilt sensors to measure the movements at the surface level as a result of this process of infiltration. Then strain gauges to record the movements at deeper levels. Now, all this equipment can acquire the data electronically and transfer to the head office for decision making.
Sir, I pardon to disturb you, sir, but your screen is not moving, I guess.
Sorry?
The screen is not, slides are not moving forward.
My slides are moving.
Okay, but stuck here, sir. Can you just like try to reshare your slide once again?
Sorry?
Sir, can you reshare the slides?
Sir, you have to stop the screen share, then again you have to share the slides.
Right. How is it now?
It is not perfect.
Sorry?
It's working, sir. You can go ahead, please.
It's working now.
Is it moving?
Yes.
Is it moving now?
Yes, sir.
All right. Okay. Actually, I didn't notice that because in my screen it is moving. So yeah. I was not aware whether the others are seeing or not. Right. Sorry about it. Anyway, so we are monitoring the moisture changes in the moisture content in the pore pressure regime and movements by extensometers and strain gauges. And all these electronically acquired, and inclinometers, that is, go to the site and observe it, the particular borehole locations. So these are some of the pictures of the water level gauges. And in the monitoring of pore water pressure, in these residual soil formations, we get layers of contrasting permeability. So we need to monitor it at different layers, having identified the critical situations through our analysis. These are the usage of extensometers. So what is shown in red is the identified landslide boundary. In the extensometer, one end should be in the firm ground and the other end in the identified failure zone. So this long tube has a wire inside. The changes in the length of the wire is monitored through this device. So we have installed extensometers at number of locations in these critical slopes. Then through research done at University of Tokyo, these tilt sensors were developed. So that is simply a rod like 2 to 3 meter long rod. And this can watch the rotation with the land side movement. We can watch the rotation at the shallow depths and also monitor the volumetric water content. We have sort of installed this at some sites and correlated that with the movements of the movements recorded from the extensometer. Then if we need to identify the deeper level failure surfaces, the inclinometer is the tool to be used. So we do boreholes extending below the potential failure zone and install these tubes, and with these probes in 2 different directions, measurements were done at regular intervals. As seen here with these 2, measurements were done at in the boreholes, lowering the probe, which could detect the movements at this level, and in the other one, the movement at that level was detected by the inclinometer inserted into the holes at regular intervals. These are some pictures of how the extensometers responded to the rainfall here. With that rainfall, that is the cumulative water, the input, and the extensometers have started to move, and tilt sensors also are showing the movements in response to this particular rainfall. Here it is sort of a little bit zoomed up and elaborated in this part of the picture. So these are the other instrument, the strain gauges and installation, that process. Now I will come to this about the instrumentation done at the Badulu Sirigama landslide. So we will talk about this in detail a little later. So this is the identified failure surface through field assessments, field visits. And so that is the axis of the landslide. You can see there are few inclinometers, the pipe strain gauges, the ground water level measurements, and extensometers extending across the failure surface. And this indicates the response of this instrument to a rainfall. This rainfall, with that rainfall, the water level has risen up like that, and there were movements recorded in the extensometers located at these localities, and movements in the other instruments here are located here. This is the movements in the strain gauges. Right. Now coming to the most important aspect of rectification of slopes. If our initial investigation results and analysis indicates a slope is unstable, then we have to attack the core reasons for instability to make it stable, to stabilize that. In the process of landslide remedial measures, the approaches or the procedures adopted are basically modification of the slope geometry, drainage, retaining structures, and internal slope reinforcements. With the rain-induced landslides, drainage is the focus, that is the forerunner, but other aspects will also be used. In the modification of the slope geometry, we remove material from the area higher up driving the landslide and add material to the toe and reduce the general slope angle. I will elaborate these with few case studies that I am presenting next. Now, our infiltration analyzers indicate that infiltration in an uncontrolled manner gives rise to these changes in the pore pressure regime leading to instability. Hence, our approach should be to minimize infiltration, minimize the loss of matrix suction, and allow pore pressure dissipation, which we achieve by improving the surface drainage and providing subsurface drainage. Now, with the surface drainage, we use cut-off drains, berm drains, etc., to drive away the water from the critical regions. Shallow, deep trench drains are also used. In addition, appropriate vegetation cover is used on the slopes or artificial slope cover like shotcrete to minimize infiltration. And the relic joints exposed should be sealed to minimize the infiltration. These show some examples of surface drainage measures adopted in the construction of the Southern Expressway. Slopes, natural slopes, were cut into steep profiles to make way for the expressway. So water coming from the hill higher up was intercepted by cut-off drains and taken away from the critical cut slopes. So similarly, the berm drains. So we have to have a drain of appropriate capacity based on the catchment area. So that is connected to a cascade drain over here. Here you see the berm drains are connected to a cascade drain. In this location, a very critical location with very high uphill up there. So there were 3 berms, the berm drains, the construction of the cascade drains are illustrated. Before the completion of the whole drainage work, there was one heavy rainfall. So you can see how the water is flowing over when the drains are not properly completed. So with the proper completion of the drains, all that water is intercepted and well directed down here with the intention of minimizing the infiltration. If you have boulder terrains, we may not be able to cut and make a drain. So we may have to use techniques like these L drains in that situations. Similarly, in this steep slope profile, so we have done a L drain connected to the road pavement to make sure that there is no flow water into the steep terrain. I have a problem with this popping up on my screen. Right, so anyway, moving to the next slide. So about the vegetation or any cover on the surface. So we try to use the vegetation cover to protect erosion, prevent erosion. But when the soil is not weathered enough, vegetation will not come up. In such situations like closely fractured rock, we may have to use artificial means like shotcreting. With the introduction of the vegetation, we can prevent the surface erosion, and the vegetation enhances the cohesion at shallow depths, and the longer roots will provide some kind of a reinforcing action, and heavy rainfall falling on the area will be intercepted by the foliage, reducing delaying the time that it comes down to the end area, and also the roots extracts moisture in the evapotranspiration process, reduce the moisture content, and sometimes inducing high suctions in that. So the introduction of vegetation into a cut slope will have to be done through an appropriate technique. If it is well weathered, you can do turfing. Otherwise, we'll have to use hydroseeding techniques. This shows the technique of hydroseeding after the spraying of seeds fertilizer and the topsoil on the cut soak profile till the seeds germinate and it is grown. It is protected by a coir mat. Here, turfing and getting it grow. So it is again protected by the coir mat. And here, a straw mat had been used to protect the hydroseeding till it gets germinated. Here, gradually, how the seeds have come up, covering the area. So those are the surface drainage measures used to protect the slopes in different situations. Now, in certain slopes, in most slopes, we need subsurface drainage as well to get the protection. So with the subsurface drainage, the movement of the water already gone into the soil is onto the slope is accelerated, and we make the water to flow under gravity. So there are different forms. So having understood the specific situation in a particular site, we'll have to get the things in most appropriate orientation to enhance the effectiveness. So we can use the subsurface drains in addition to the surface drainage measures like cutoff drains and trench drains. The simplest form is unidirectional pipe, perforated pipe inserted into the slope. Now, coming to a specific application in Sri Lanka, the Vatavela landslide. Dr. Bandari was heavily involved in this rectification work that occurred in the main railway track from in the upcountry, Vatavela to Galavoda, around 150 meters of the length. Now, due to the slope movements, there is subsidence in the railway track, which cause this kind of derailment. With excessive investigations, collaborative investigations through NBRO, UNDP, and all that forces, we have identified the failure surface, which is at a depth of 30 to 35 meters in the colloquial layer. Now, this the groundwater table is somewhere there during the dry season. In the wet season, it can go up. With that, slow movements are initiated here. There is some rock here which prevents the complete collapse. So with the accumulated set of movements over the years, shear strengths here have come down to residual values. So the critical aspect is to prevent the perpetual development around this identified critical surface, which was done by installation of directional drains. So that was the first time the directional drains were used in Sri Lanka. We got assistance from UNDP and the Chandler Limited and Australian contractor did the job. So these perforated drains were drilled from a lower level, coming up to the surface. High-density polyethylene HDPE pipes were installed in that. There were perforations in the pipes at various at regular intervals. They could withstand strains up to about 800%, so that with little movements, there will be no deformations. This shows how the upper level, how the pipes come up off the ground over here. In addition, there were pumping wells and ejectors to pump the water out in case they are not working or till they were installed. But pumping water out regularly would be quite costly. Finally, these directional drains did the job. So there were 13 such directional drains. So that is the lower end, spanned over the full plan area of the landslide. And these are some photographs were the ejectors, the pumping wells, and the lower part of the drainage, the drainage outlets, which I took in 1995. This was completed somewhere in 1993 or 1994. We revisited the site in 2012. This is a picture in 2012. It is still working, but we identified there is some blockage in these drains, and NBRO with some JICA assistance cleaned those drains to improve their performance in 2023. And these are some pumping wells that can be used in case of an emergency to lower the groundwater table further. Then coming into another landslide in the road network that was improved by drainage only. Earlier, I showed the instrumentation done in Badulusegama landslide in the Over province. So extensive investigations were done there with JICA assistance, geomorphological, borehole surveys, geophysical surveys, etc., to identify the failure surfaces, the subsoil conditions, and so forth. So this is the subsoil condition derived from that. Now, these investigations indicated there are 3 different failure surfaces in that, which were named as upper slide, middle slide, and lower slide. Some are shallow, 10-15 meters range. And with the rise of the groundwater table during the rainy season, there are movements taking place in these slides. So the process for rectification was drainage only. So this is the identified landslide boundary. There were these surface drainage measures in the blue color. Then fan type drains were installed from top level to the bottom level. So that is at the top level to the bottom level. Each fan containing about 9 drains of length 40 to 60 meter were installed at these different elevations to facilitate the quick pore pressure dissipation and make the slope stable. So these are some pictures of surface drains. So this is how these fan type, subhorizontal drains were collected at one point. Water accumulated there is drained away through the pipes under the ground. Now, with many of these projects, we did some extra bit of research to get a better understanding about the situation and the rectification process. As a result, number of young NBRO engineers were able to do master's projects and gain additionally from that. So in this Badulusegama, with the Badulusegama data, we studied the process of the drainage, the construction effect of construction sequence in that in 2 different alternate ways, that is 2D analysis with geoslope software and a 3D analysis using Plexis 3D. So in the geoslope analysis 2D software, we use this identified failure surfaces. We use these identified failure surfaces in a pre-specified approach using the Spencer's method, and the effect of stability was evaluated. In the Plexis 3D, without using predetermined the failure surface, we model it using the stress C5 reduction technique, and showing some results of this 2D analysis. So these are the drains that were installed. We studied the construction sequence of installation of these drains. Can we do it bottom up or top down? What are the differences in behavior when it happens when we install from the bottom up and the top down approach? So that is there was a 3-day time space between these the installations. So that is the top down approach, from here bottom up approach. And in that, with the top down approach, you could see the upper side and the middle side factor of safety improved very fast. In the bottom one, improvement was seen only after installation of the drains at the lower levels. In the bottom up approach, again, the stability of the bottom level improved fast here, and the upper one improved only through halfway. So we could study about the effect of the drainage installation on the stability of different sites and work out what is most appropriate. After that, we studied what would happen if the rectified slope is subjected to a critical predicted rainfall on the site. So it shows how with this heavy rainfall, how the factor of safety initially didn't change much, but with the very heavy days, so there was a drop and it catches up very quickly because the drains are working. We did further analysis, taking the three combined failure surfaces as a composite failure surface, observed how the factor of safety will improve gradually with the gradual installation of the drains, either bottom up and top down approach, and how the porpoises were changing. And on the composite surface also, we applied this heavy rainfall and see how the slope will respond to that heavy rainfall. So with days of low intensity, there were still developments. The factor of safety is still developing because of the so many drainage paths available, and it experienced a reduction with the heavy days over here and recovers very quickly. In some slopes, we have to use the structural measures in addition to these drainage measures. They may be earth retaining structures or internal slope stabilization. Some of these cut slopes with the expressways, we have done vertical cuts, near vertical cuts, and done retaining structures. So we can do near vertical cuts during the periods of dry weather. You see, it is quite safe. We can do the cut during the periods of dry weather and install these retaining walls. So this will not be stable during a rainy period. So this is a Candice Pool, which was hampered by landslide events. So this slope was stabilized by construction of a gravity wall after cutting the slope during a period of dry weather. You can see the drainage layers and all. We use the structure with back batter to improve the economy of the wall. Then we have used the soil nailing in many number of situations. With the soil nailing, when the slope starts to move, a tensile load will mobilize in the reinforcement. It will increase the normal stress and reduce the shear resistance to be mobilized, thus increasing the factor of safety. So we have used this nailing at number of locations. So here it shows the process nailing and grouting and connecting them up, connecting the nail heads with beams and shotcreting. Now we have to do the drainage measures along with soil nailing. So here in this cut slope in the Southern Expressway, nailing was done, but it was close to a valley in this hilly terrain. So the drainage in the valley was improved by these basing drains and then cut off, then the cascade drains going down the slope. This was a sort of slope in the Southern Expressway with drainage measures, but there were some problems in the maintenance. It was leaking, and one morning there was this crack appearing. So by that afternoon, the whole mesh has come down. You can see the failure surface is not deep, it is quite shallow. Soil is relatively dry, water table has not risen. The saturation of the material has caused this destruction. Then the face left behind by that is quite steep, so that need stabilization. So we design soil nailing to stabilize that part, and to economize on that, we put a toe retaining structure, gabion wall, and backfill. So this shows the plan. These are the green ones are the anchors, because the nailing, when the nail length exceeded 15 meters, we said we will use anchors. The other part are the nails. You see in the cross section, these are the anchors, and here are the soil nails, the gabion wall constructed in front, and this is the construction sequence that is there. In the drilling for this nailing, we observed boudinage structures, but we'll have to drill through that. And also we observed a joint pattern like that. This was earlier known, but it was confirmed here. We found that there is water under high pressure in these relic joints. So when the drilling was done, there was mud coming up at high pressure, covering these people in mud like that. And uh, when the drill holes were grouted, there was grout coming up from the other holes already drilled. So we have to spend a lot more grout volume than what is required. And with the construction sequence, we did the sub-horizontal drains after completion of all the grouting. Otherwise, drains would get blocked with the grout with this interconnected joint planes. We studied the infiltration through these relic joint planes and see the effect. And from that, we could see, we back analyzed the failure. We found that the failure will occur with the presence of relic joints. If the relic joints were not there, then there will be the failure factor of safety will not come down to 1 with the rainfall that experienced prior to this landslide. So this is the finished structure. Then subsequently in our nailing work, we try to avoid full face shotcreting. We connect the nail heads through beams and connected them through high strength tensile wire, and vegetation was allowed. Here you can see that. Here, because of the presence of closely sort of fractured rock, we have to do the shotcreting. Here we see connecting of the nails through beams and getting the grass to grow in between. And so that is the process that we adopt in current projects. So here you have a nail head or a spike plate in here. When the beams are not used, you require connecting wire, the tensile strength required to be much greater. And so some of the things. Now, I'll just take this particular slide. I'm just exceeding my time because there was this disturbance in between. Now, here, they have, RDA has widened this slope, which is a former landslide without any geotechnical input. So that reactivated the landslide, and then NVRO got involved here. So there was this marshy area, water table is high further behind. This is the thing that they were trying to widen. So we studied the subsoil profile and the characteristics through detailed investigations. So this was the subsoil profile, and this is the axis along which the major slide is happening. And they need to widen the road. So it has to be excavated back like that with these drains and nailing. So this is the final design, but we have to pay greater attention as how do we arrive at this. The construction sequence should be analyzed in detail. Before doing any nails at the top, we need to get the water table lowered by surface drainage and subsurface drainage. Only that will permit this drainage. So we do that in stages. So in the stage 1, groundwater table is lowered, and through surface drainage measures and some subsurface drainage measures, this nailing was done. Then stage 2 and stage 3. So these were the pipes installed for subsurface drainage. And you can see this trench drain with the travel pack drain underneath installed there at the top level, right? How the water is draining off, facilitating the lowering of the groundwater table, nailing, and the nail heads were connected by concrete beams, and vegetation was introduced in there. So we studied the effect of these processes during these construction stages. If there is a rainfall of this intensity, the critical design rainfall happens. So we saw that without the soil nailing, so these blue ones indicate the effect of, say, the no drains, no nailing is the bottom one. Surface drains with no nailing. So the blue curves basically indicate the variation of factor of safety if there is no nailing. So you would see that in the 3 construction stages, we cannot get to a good factor of safety without nailing. So with the nailing and surface and subsurface draining, you can achieve a high factor of safety, maintain a very high factor of safety, even with the presence of this rainfall. So for the stage 3, and this summarizes the final situation. With the surface and subsurface drains and nailing, we could achieve a good factor of safety. We could maintain a good factor of safety even with that rainfall. So if we do not use subsurface drains, greater length of nails would be required, which will be uneconomical. So this further research that we did with this data indicated that we have to emphasize on the drainage measures when we are inputting these reinforcing techniques to make the thing very effective. So this is the final produced thing. And the last case I will present very quickly, another road failure, landslide at road at Kahagalla. So with the detailed investigations, the subsoil profiles, the failure patterns were identified. And there were 4 failure surfaces like that identified. And the response of the various instrumentation to the rainfalls were identified prior to the construction. And the remedial measures were removal of some material from the top and getting a road toe embankment and drainage, fan type drainage through drainage wells. Here the failure surface is deeper. We could not do the fan drains as in the Badulusirigama. So these fan type drains were implemented from drainage wells, and there is some anchoring here. This is more clear in the cross section. So these are the drainage wells from which fan type drains were installed, anchoring at the bottom, that is the road level. And this weight is removed and a weight is added at the top. So these are the measures, pictorial view of different measures adopted, anchors, and the drainage well and fan type drain system extending from the drainage well. Right. So that brings me to the conclusion. The sloping grounds in Sri Lanka are made of residual soils, rocks at different levels of weathering and colluvial soils. So highly heterogeneous conditions exist there in this picturesque landscape. So these challenging situations caused by infiltration but will taken care of by innovative approaches. As you could see, we have done the hazard zonation mapping. There is monitoring through rain gauges and also subsoil monitoring. The design of these rectification measures were done by geotechnical professionals attached to the NBRO. As a team, we visit the sites, potential sites, comprehend the geological conditions, plan the necessary geological, geophysical, and geotechnical investigations, and monitoring required, and come up with a designed solution. Finally, we go to the site and verify the disaster design solution proposed. In this process, we have got assistance from NGI, Norwegian Geotechnical Institute, in training NBRO officials and getting the drones for the surveys to get the profiles, and GPR and other modern equipment. JICA has also contributed a lot in training NBRO professionals, instrumentation in slopes, and runout area studies, and so forth. So we have further plans to introduce global monitoring of the subsidence slopes with techniques such as terrestrial photogrammetry, LiDAR survey, and INSA satellite techniques. So our efforts to reduce the risk of landslide in the country will continue by incorporating emerging new technologies. Thank you very much for your patience listening. So I have taken a little extra time because of this disturbance. Anyway, sorry about it. Thank you.
Very interesting lecture, sir. Thank you very much. Really, theory came into the field and fully implemented, and we are seeing the result. So we will take up the question after the second lecture. So
okay.
Now we are having Honorary Secretary of Sri Lankan Geotechnical Society, Professor Udeni Navaga Mua. He is a professor in the Department of Civil Engineering, University of Moratuwa, Sri Lanka. He is having a very vast experience of teaching as well as industry exposure. So now I'd like to invite Professor Udeni to introduce our second speaker, Professor Nilima Satyam. So please, Professor Udeni, sir.
Yeah, thank you, Dr. Singh. It's a nice meeting all of you there at this inaugural joint webinar series. Thank you very much for inviting me to introduce a very well-engaged personality in the field of geotechnical engineering, Professor Nilima Satyam. She is a professor in the Department of Civil Engineering at IIT Indore, India. She garners her expertise in geotechnical, earthquake engineering, landslide hazards, and rock mechanics. She is an INSA associate and SCRB Power Fellow and has worked as a consultant to major infrastructure projects in India. Her prolific publication record with 110 international journals and several conference paper book chapters underscores her significant contribution to the research and development. She has also worked as an editor to journals such as JRMGE, Scientific Reports, IGJ, etc. So with this very small introduction, I would like to invite Professor Nilima Satyam to talk on rainfall-induced landslides, monitoring and mitigation measures. Over to you, Professor Nilima.
So thank you so much, Professor Devi. First of all, I extend my sincere thanks to IGS President and Honorary Secretary for initiating this webinar between Indian Geotechnical Society and the Sri Lankan Geotechnical Society. It's my honor to be the first speaker of this webinar series. I also very honored to have Bandari sir and Madhav sir attending this particular talk. So thank you so much, sir, for attending. And so good evening to all our IGS colleagues and Sri Lankan Geotechnical friends and also the Nepal Geotechnical Society friends. So I'll try. I'm sharing my screen over here. Is my screen visible?
Yeah.
Yes.
I'm trying to use a different iPad of my daughter. Actually, I had some issue with my mic in my laptop. So I'm sorry for it. Is my screen visible now?
Yes.
Thank you so much. So my topic for today is like landslide monitoring and modeling. I had extensive talk and with several case studies from Kulatirka sir just before us. So sir has taken that in the slope scale. So but my presentation is on the regional scale and the local scale. So in this particular presentation, I would like to highlight two aspects from my research. One is like monitoring aspects and what we have been doing for development of the early warning system. The second one is the modeling aspects. Here, modeling for debris flows, so which were very predominant in the Western Ghats of the country, especially in the state of Kerala. So these are the two case studies which I'll try to brief here. First one is the Eastern Himalayas, and the second one is on the Western Ghats. So coming to the work that I've been working on landslide research from our lab, Geotechnical Research Lab at IIT Indo. We started this work sometime in 2016 with the support of DST, that is Department of Science and Technology, Government of India. And these were the areas we have been working in different aspects of landslides, not just landslide forecasting. We are basically working on majorly three aspects. One is like landslide forecasting and monitoring and modeling. Because monitoring for a larger area, especially slope scale is possible, but if you want to monitor for a large area, it's been very expensive, and also practically there are several issues. So what we have been doing is like we are using the monitoring to validate our forecasting model, so that our early warning system is like, we have very or minimal false alarms. So first of all, like, in the Western Himalayas, we started with Kalimpong. That is our first area. As like Pulitevika sir mentioned it, like I use that monitoring system which has been developed at Tokyo University because I was a JSPS fellow there. So the same system which has been developed by Uchimura Sansei and Tawata Sansei, that's I procured the same thing there, and which we put it up installed in 2016 post monsoon at a place called Kalimpong. That's my first case study of this particular talk. And we are also extensively not only tilt sensors, and we are also monitoring for a combined hazard, especially for the landslide region in the area called Joshimath. For the last 2 years, we have been monitoring with a very dense network of sensors. And again, it's been supported from NRDMS, the Government of India, where like we have sensors both inside the borelog at around 15 meters and also on the surface sensors. And that is actually, since it's a combined hazard, considering both seismic microseismic monitoring is also been there along with the rainfall. So that particular part is something which we are ongoing work. And the third one is the Idukki and Wayanad. These are the two districts in the state of Kerala, which is worst hit state since 2018 with respect to landslides. So extensive, debris was very predominant type of landslides that has been observed during our field visit. So we've been working on two aspects here. One is like the landslide susceptibility map, which has been developed by the State Disaster Management Authority, that is Kerala State Disaster Management Authority, was not actual there, because wherever the susceptible zones were being marked in 2018, it has been observed that there was no landslide, and where there is no susceptibility, so there is a huge slides have been occurred. So we were given a task of preparing a dynamic landslide susceptibility map at the panchayat level, which we have done. And since the debris flows were very predominant in this particular part of the country, so we worked, and again supported from the ISRO. So we have developed a debris flow model. We had some tools like ramps, etc., which have had some challenges or with respect to the data. So what we have done is like ISRO want us to track the debris model along with the entrainment using the satellite data. So these are the two things which I will be explaining. Coming to the overview of this particular presentation, as I said, I had two case studies in this particular talk today. So one is like rainfall thresholds for the warning system, which we have built it up for the particular small region, like which is around 1,200 square meter area. It's a Kalimpong, it's a town. And this town is very beautiful in the Darjeeling Himalayan regions in the state of West Bengal, where we have developed the local scale forecasting models and using different forecasts, which I will be explaining. And then part of this area we monitored using the tilt sensors, and they were initially we installed 8, and then later we extended to 14. And then we using this monitoring data, we have validated the forecasting model and finally developed an early warning system. And this early warning system has been handed over to an NGO called Save the Hills, and which has been a lot of training they have done, and people are using it also. And then second case study is, as Mostly, I would like to emphasize on debris flows. So by taking the case study, we have done at 5 different, because the debris track, the length of the debris track in this region was like between 3 kilometers to 3.5 kilometers. So we have done a lot of geotechnical investigations, geophysical investigations, and also like, we have done the modeling aspects. Okay, so landslides, like Sri Lanka or Nepal, is one of the very big geohazards which we are doing, most damaging geological hazard in several areas of mountainous regions in the country, both Eastern Ghats, Western Ghats, and the Himalayan regions, which is causing not only loss of life or destruction to infrastructure. Another very important thing is like people are losing land, especially when we did our field visit in the town Kalimpong. Farmers were literally becoming coolies after a slide. So it is a complete livelihood and entire things have been lost, and they are landed as coolies somewhere in Calcutta. So up to like 15% of our landmass vulnerable to the landslides, and major landslide triggering factors we know this is like rainfall and also earthquakes, in addition to some of the man-made factors like mining or like illegal construction activities, etc. So and of course India being densely populated, and various large scale infrastructure projects are also present. In Kalimba, people were started building 10-story buildings, hotel buildings along the slopes, which are very, very present. So some of the photos I'll show here, and several areas are in a developing stage, and also a lot of hydropower projects have been there in some of these landslide regions. Therefore, there is a need for combined landslide hazard assessment and development of warning systems, especially for this region. As I said, basically rainfall, earthquakes, and entrepreneurship activities, they are the triggering factors, and which includes mining, which is very common in the Western Ghats, especially the Kerala, which we observed, hill cutting, illegal constructions, and of course some sort of other factors. This one I'll skip it up because some of the aspects already discussed in the previous talks, which are the triggering factors, especially for the landslides to occur. So now, like when we go to the field, like the signs of landslides, like we do observe a lot of open cracks or accumulation of the water on the top, and seepage aspects or some sort of springs we see, tilting of the slopes or the tilting of the trees, and some poles, etc., fences cracked or the distorted structures. So these are some of the signs of the landslides which we generally see. So with this introduction, I just want to start the forecasting what we have done, and also for real-time monitoring which were done in the first case study. And here two things have been done. One is like rainfall thresholds. So in the literature, we do have several models, starting from empirical models to highly advanced algorithm models. So what we did is like we applied all the models in this town like Kalimpong, and we want to see which model is going to suit well for this one, because it is all site specific and also depends upon availability of the data. So if you look at the thresholds, so thresholds are the conditions which defines the state of change in any system. So in this case of the landslides, which can say that if it exceeds the rainfall threshold condition, rainfall is also like earthquake. It is also highly dynamic. It's not just only rainfall intensity or duration. We would like to take several other parameters of rainfall, including antecedent rainfall, etc. So it indicates that the landslide will occur in that study area or not. So rainfall is usually defined using 3 parameters like event, duration, and of course intensity. And while event is the total amount of the rainfall that happened during a specific period, and intensity is the rate of rainfall that is defined as the ratio of the event and the duration. We are trying to look at the probabilistic aspects also, wherein like combined and controlled thresholds were developed. Don't know why this is issued. So this is actually the rainfall thresholds and the warning system. We use like ID thresholds, and which is a mostly deterministic. I think it was showing blank because I'm using a different browser over here.
Shall I share my screen now?
It's okay. So this is fine, right? I'll just explain. So in the ID threshold, which is generally a deterministic way of making the thresholds, we also use the ED thresholds, which is a probabilistic, taking the uncertainties as well. And the probabilistic models, like based on the rainfall, only like control parameters have been added. So which considers both the triggering and non-triggering rainfall events. So probabilistic models were also being considered. Process-based models. In the process-based models, precise field-based informations are required. So we try to collect a lot of data from the field and suitable for the smaller watersheds as well. And since this is an area wherein like we try to develop the warning system at the regional scale, so we applied that as well. And Sigma model is actually a statistical model using a kind of decisional algorithms, and which considers both short-term and the long-term rainfall. So which we try to do here. And then another algorithm-based models like matrix-based approaches by integrating rainfall thresholds and the field monitoring data. So we try to use that also for control false warnings. So all these threshold models which are there, so we try to put it on the use that on the particular study area, which is a Kalimpong, which I'll explain one by one. After that, we started instrumentation also on the day one of the starting of the project. That was in 2016 post monsoon. And since we don't have the pre-monsoon data, we discarded 2016 data. And since 2017, we started monitoring the site part of the town, the western part of the town, which is a Chibo area. And then, we started validating the forecasting models and try to build the warning system. So this is actually the overall methodology that what we adopted. So this is the location details of the study area, the first study area. So this is one of the hill stations, and it is like a curved tabletop. And at the either sides, there is two major rivers. One is like Reli River, and another is a very big Tista River. And there's a lot of toe erosions also observed. And this particular photo, which is on the top, so this is actually one slope on the western slope. So where we monitored. So these blue lines are the streamlets, because there's a lot of built-up area is coming up on the top and also along the slopes. So these streamlets are joining, and they're going and joining with the down at the toe part of this either side. And then when they are going down along the slope, a lot of erosion was also observed. And the white colored line, whatever you are seeing over here, it's our trek line, wherein like we trek down, and whatever the white dots with buildings or some small structures, there are like school buildings where there were cracks observed in the floors, and there was some army establishment also in this region. So whatever that oval shape orange color has been marked, so it is actually very, very fragile slopes, wherein like after our field visit, we decided that we would like to instrument instrument this particular location. So, and when we started this, so this is actually the topography and some of the hydrological aspects. So as I said, like built up area has been increasing, because it is one of the educational hub and also tourist attraction place in this part of the country, wherein like every year several people visit, and there are a lot of educational institutions in this region. So hotels and other establishments have been increasing for quite some time. So people were building without proper guidelines as well. And whatever the road you are seeing, it is actually the national highway, and which is the only road connecting to this particular town. And failure, if you look at the failure mechanisms, and most of the failure in this region are not sudden failures, they are progressive failures. And the local people, they used to tell, like, in this particular area, it's very interesting because people in this region speak Nepali. They don't even speak Bengal or Hindi. So they used to say that if there is a crack in this year, and next year this may slide up. So a lot of progressive failures have been observed. And coming to the thresholds, so we started with the ID thresholds. I think there's some distortion. Okay. So we started with the ID thresholds. When we started the work, there was only one rain gauge operated by the Geological Survey of India at the Tista 9th mile. And this data, we used to get the daily rainfall data. And we started collecting the data from 2010. And then, we used, landscape inventory also, we started building it up, and then we worked on the data for almost 6 months. And after doing the ID thresholds, we found it out, I is equal to 3.52 d to the power of -41 was the threshold line for both short term and the long term. And then we applied the 2D and one-dimensional probabilistic approach, using Bayes approach. In this, probabilities are determined using the available rainfall and the landslide data, use Bayes theorem, and the rainfall values are collected from the automatic rain gauge, so which has been there at Traki Bazaar in Kalimpong. And then the rainfall parameters, what we use for calculating the probability or the mean intensity, rainfall duration, and of course the event rainfall. And the probabilities are determined using 1 and the 2 dimensional as control probability. So like if you see here the probability of P and L, so probability of rainfall event of degree when B, that is a landslide occurs, which is also the likelihood. So after doing the probabilistic studies, then we also applied the hydrological models. Hydrological models, actually these are all mathematical models, and we use the flyer method. Here it calculates a mathematical function called mobility function, and then the mobility function is derived by linking the rainfall intensity and the filter function to determine the slope stability. And in this hydrological model, that is a flyer, this mobility function has been considered as the convention between the rainfall and of course the filter function. So what we did is it is a site specific parameter, because we have to take a lot of geological data and geohydrological data also for calculating this mobility value. After calculating this mobility value for this particular site, so what we did is critical mobility we established. So for this one, there was one major landslide that happened in this Kalimpong town on 1st July 2015. So we have taken that data to calculate the mobility function of this particular region, and which we got it around 4.72. So that critical value, we used it, and different levels of warning. Like here, if you see here, 0.8 times of the critical value, we use it for generating the alarm, 0.6 times as the alert, and 0.4 times as the attention. So this is actually continuous curve. Now we have a small app also wherein you can install, and this based upon the rainfall, the curve dynamically get be plotted. So when it plots, if it hits the attention line, then people can be attend to, or if it touches the red line, the local administration can give an alert, and of course subsequently alarm can be generated. So but the most what we found is that this particular model was it was giving only 67% of the accuracy. So the lot of false alarms was generated. So though it was not it was giving very good levels of warning, 3 different levels of warning, so it was not implemented. And the fourth one, what we have done is a process-based model. In the process-based model, we use the standard TRIGRS method, which is transient rainfall, infiltration, and grid-based slope stability numerical model, which computes the change in the pore water pressures and also the changes in the factor of safety because of the rainfall and the infiltration. So this is it uses the infinite slope model for evaluation of the factor of safety in each pixel of the mesh, and the application of this was used for historical rainfall scenarios to compare the results with the available landslide database. So then the rainfall events, whatever we chosen as input for calibration, was again whatever happened in the 30th June 2015. So we use that data because that particular event has a proper record. So and then the rainfall during that period was more than the average, and which caused almost 18 landslides in the entire Kalimpong town. Then we compared the results of this numerical simulation with the inventory between 2010 to 2015, and then it turns out that the model is able to reproduce the reference event quite well and identifying the area most affected by the shallow landslides. And then the accuracy of the maps, that whatever produced from this model was verified using a receiver operating the ROC curves, and then the results showed that the model is capable of forecasting the landslides from a temporal perspective because of its corrective prediction, which was around 54% in this particular case. And then we also use some of the advanced models, as I said, Sigma model, which is an algorithm-based model. And in the Sigma model, so in the Sigma model, you can see the flow chart for this one. So it's like a trial and error model where it will calculate for different sigma values and check the event and rainfall data happen. So if you see on the curve over here, which is between the cumulative rainfall versus sigma curves, so for different sigma values starting from 1, 1.5, 2, and 2.5, whatever. So we done the analysis, and based on the analysis, we try to generate the 4 different levels of alarm. We also try to compare that comparison of this model with other empirical models, and here is the statistical analysis that attributes what we got for ID, ED, and sigma model, all like with a true positive, false negative, and the true negative. And the efficiency we try to calculate that for all the 3 models, so which wherein like we got the highest efficiency with this sigma model. And what we have done is like this model has been developed at the University of Florence, like where like what we integrated our monitoring data into this sigma model, which I'll explain in the next slides. So then coming to the second part of the work, monitoring at Kalimpong. So this is actually we used tilt sensors. We initially put at 6 meters, around 1.5 meters from the slope, because this is the western slope. You can see the elevation profile of the sensors that what we have done, the sensor location, 6 different sensors. And here what we found is like not only installation, the safety of the equipment was also major concern. So most of the sensors we instrumented in the private areas, especially school premises and the nurseries, and of course some private houses, etc. So we try to instrument that at around 2 meters. Along with that, we also instrumented a digital rain gauge. And then since 2016, we started putting the getting the data for every 10 minutes. So this is the data. So you can see here some of the time histories for the 3. I put here for 3 years: 2017, 18, and 19. And then this is the precipitation rainfall details along with the tilt data, and rate of tilt has been calculated at all the slopes. And in between, like in compared to 2017, 2018, the rainfall intensity was less, but more landslides has happened. And in 2019, what we observed with the rainfall pattern up to August, the rainfall was like not so significant, and suddenly there was a huge rainfall started happening. So, and we try to compare that with the ground signatures as well. It's you see in the left side of the slide. So there's a lot of subsidence kind of formations we can see here. And then this is actually, and then we try to look at, and we lost 2 sensors in the first year. And this is actually data from the 2017 to 20. And we monitored 5 years actually. And then after that, 3-year data we used for training, and then 2-year data we used for validating our models. So totally 5-year continuous data has been done for this particular town in developing the warning system. So these are the 3 sensor data, and then we try to zoom in and check that data with the real ground signatures, because we try to have a volunteer from this particular town as well. And then after this, we would like to see, I think there is one more bar chart on the left side, which we missed it up. What we did is like we want to do the performance enhancement of this rainfall thresholds by integrating the actual ground tilt data. So if you see here, what we have done is like after getting the rainfall thresholds, we integrated that because that is a conventional rainfall thresholds, and which gives the higher number of false alarms and higher number of missed alarms also. So, and then from the field monitoring, that is the second part, this process based models, and we had a higher number of false alarms. So we integrated both the thresholds and the field monitoring data, so that the performance enhancement was being done by combining both the things, and then it reduced number of false alarms and the missed alarms, and so that the efficiency of the warning system was improved. So you can see that from the graph that based on the performance enhancement, we got like it has been improved when we try to integrate that with ED and the tilt. So this is again the integration of the sigma model with the tilt data. So we try to look at the efficiency to AUC curve, and then we try to make an algorithm for integrating both sigma model, because we had access with the sigma model as we are collaborating with the developers. Then we integrated our real-time monitoring data into this, and then tried to build a effective warning system. So this is the final one which we made it. And the efficiency and the likelihood ratio were the attributes which we use for comparison of different rainfall thresholds. And for Kalimpong, after doing carrying out the thresholds for using all the threshold models, so what we found is the sigma plus tilt it outperforms all the models, and it can be proposed as a satisfactory component in the landslide early warning system. And then it also, another good thing is like it considers both the short-term and the long-term rainfall patterns, because in this particular town, there will be rainfall continuously for 4 or 5 days also. So we want to consider both the short-term and the long-term patterns of rainfall and the tilt rates, and hence the issues of less false alarms has been done. Currently, what we are trying to do is like we are also developing an automatic alert system based on the prototype focusing format, and we had 4 different levels of alert that has been like, one is red, orange, yellow, and the green. 4 different we have considered, and in this particular thing. And the second one, the second case study, I'm extremely sorry, there is some issue with the browser. Second one is on the Western Ghats, wherein like I have taken 2 districts of Kerala state, that is Idukki and Wayanad. In this one, what we have done, we have a different approach here for Idukki and Wayanad. That what it's a little bit complex methodology, because due to the vastness of the study areas, they are not small areas like Kalimpong. So they're huge, and also not only that, the data from 4 rain gauges were considered for both the districts, and I should acknowledge the data that is given by the dam authorities as the rainfall varies across the districts. And along with the selection of the appropriate rainfall threshold, selection of the rainfall parameters also become critical, which we try to consider over here. And the forecasting is conducted on the regional scale, and we didn't do any field installations. The temporal forecast was carried out using the rainfall thresholds, whereas the spatial using the landslide susceptibility maps. And both were matched using a matrix-based approach to develop a spatio-temporal landslide forecasting framework, which is one of the very effective, and of course, they are being used at panchayat level. That is more important. So what we try to do is like whatever the susceptibility map or dynamic susceptibility map which we developed is at the panchayat level, so that that administration can give the warning with the at least like 4 or 5 hours before. And the site-specific studies were conducted for debris flows and the most catastrophic landslide type that we observed in this particular region since 2018. And the runout models were further integrated with the landslide susceptibility map, so that we can develop a detailed hazard map considering the landslide dynamics. So this is the overall work what we have carried out for this particular case study. So this is the study area details, and since 2018 there's a huge amount of landslides, like sorry. Okay, so in this particular area, you can see here Western Ghats experience an annual rainfall as high as almost like 5,000 mm here because of the southwest monsoon and the northeast monsoons. So in 2018 itself, there was like several districts of this state has been severely affected and displaced almost 1.4 million people, and several people have lost their life. So here also we applied all the thresholds as I just explained. So sigma model, ID thresholds, CT thresholds, and the probabilistic thresholds. In addition to these are meteorological models thresholds, and in addition to that, we also try to hydrometeorological threshold models using the probabilistic approach. Then, since like we got a good data, the extensive data we could collect it from this study region, especially landslide inventory data has been prepared. I'm sorry, there are some equations on the left side which was not visible over here. So what we did is like the condition used for check the high and the moderate criticality cases were being evaluated, and that has been applied for this particular 2 districts also. And unlike the first study area, because the area is small, here what we did is like entire districts we divided into different sub-regions, and then we tried to apply the model because there's a lot of changes with the geological and geomorphological details, including geotechnical data. So for every region, we tried to do the R11, R12, whatever it is. So these are the different sub-areas in each district, which we tried to find out the threshold. So that means like it is not like thresholds have been done basically based upon the different sub-regions in the each districts of these particular 2 districts. And again, ID thresholds have been applied, and whatever the data plotted in the ID curves, as you see here, and the best fit line is calculated using the least square approach. Then the probability distribution function is fitted using the Gaussian functions. So then we derive different threshold lines. So based upon the shift of the data from the specific line. So for both the districts, we have tried to look at both the ID thresholds and the ED thresholds. And the probabilistic, that is like approach, was also been applied here. Like this is the probabilistic approach. So 1 and 2 dimensional to understand the conditional probability of this study region. Then we also try to do the quantitative comparison to understand the efficiency of the threshold models. So you can see here ED thresholds, because it is mostly probabilistic way. So then empirical ED, probabilistic ED, and ID. Then like also the probabilistic method using the Bayes theorem. So these are the, for Idukki region and the Wayanad region, we try to see the ROC cause at the regional thresholds derived from this data. And then next step, what we driven is like data-driven landslide susceptibility map. So here, what are the study that focuses on developing the susceptibility maps for Idukki using different machine learning approaches, because we got a huge data, and it's not like multiplicity of the data was absorbed. Also sometimes like some patches, some areas of the districts we could not get data. So there are a lot of issues with the data. So what we try to do is like we use different machine learning approaches also, and the procedure is represented as it's shown in this particular figure. And the first step is like we prepared the landslide inventory, and the data has been prepared using the Google Earth images after August 2018. And then it was in good agreement with the recent data that is published also. The landslides were represented using the point data at the crown of each landslide, as well as in the form of polygons. So here point data and polygon data both have been considered, and the landslide conditioning factors that are selected for the study area, including elevation aspect, slope, geology, and other factors. So all the factors have been considered. Then normalized difference, vegetation index, and the stream power index SPA was also being taken care. And hence the factors, whatever we selected, considering the different aspects that may trigger landslides, and we try to consider what is the condition of the landslides to occur over here. And then after getting this data, we try to do the sampling and the pre-processing, and this procedure is represented here as is shown. All the factors have been considered, and we try to look at both the point data as it's shown here and the polygon data. So the left side of the figure, February 2018, that's a point data, and the second one was a polygon data. So both the data were considered for doing the analysis. And so we applied different machine learning approaches, techniques to solve the problem involving this big data, where there was a limited knowledge on the theoretical past. So what we did is like ML models are highly suitable for solving these nonlinear problems. So we applied 5 different models, and they were widely adopted, especially in the landslide susceptibility mapping as well. So here are the different 5 models we applied, and this is data from the RF algorithm and also the K-fold. Then we try to look at the effect of spatial resolutions. So here, like we used to apply these 5 different models and on all the 2 different districts, both Idukki and Wayanad. And this is the DMs derived for different layers, elevation, slope, aspect, TW, and SPA. And we try to see at 2 different resolutions, because whatever the DM we got, it is 30-meter resolution. So we try to use 30 and 12.5, and then we have done some drone surveys also to make 10 centimeters. And then coming to the performance analysis, the results of this machine learning algorithm, whatever was first evaluated using the point inventory data, and of course 18 trials were run for each algorithm, and by using number of folds for cross validation. And then it was noted that in all the algorithms except the random forest, the 12.5 meter data was clearly performing better because of its high resolution, because of its quality of the data, and there were clear implications that the polygon data performs better than compared to the point data. So this is actually the first kind of study where the data has also been divided both based on point data and of course the polygon data. So this is the data-driven approach using RF model and whatever the classification we have done for both temporal probability. So then we integrated both the temporal and the spatial probability to generate the warnings. And then this is for the Idukki, again for RF model. So with the 12.5 and 30-meter resolutions, and same thing for the Wayanad. And finally, this is the proposed forecasting framework which we have done for these two districts. This is the dynamic landslide susceptibility map, which was done at the panchayat level, very specifically because KSGMA want us to develop at the panchayat level. It is not easy to generate a warning. So, or even finer ward level maps to issue that alerts. So, based upon the rainfall forecast and the soil wetness data. These maps were based upon conservative landslide susceptible map and of course the operational purposes. So it was reclassified after consulting with the KSGMA. The proposed method here used is to issue alerts for each panchayat and the ward based on both spatial and the temporal probability of occurrence of the landslides. So this is the spatial temporal forecasting framework which we used and developed for and it changes with the time. So it's very dynamic. So this is another interesting thing I can say that what we have done for the debris flows. So in this state, especially in these two districts, as I said, like a very predominant type of landslide which has occurred was like debris flows. And to understand the subsurface profile, detailed geophysical investigations using ERT, and we also done SPT. We have done bore logs were conducted at 5 different sites selected in these two districts. Vertical electrical surveys using 4 electrodes was conducted, and along the stretch, it was almost like 3 to 3.5 kilometers. Some part of the debris track was also in forest areas where we need a lot of permissions, which was being done. And so I'll just go through that what we have done. So we have done several field investigations and we collected the data samples and done the laboratory investigations also at these sites. And then we have done the numerical modeling. As I said, the commercial software ramps, so it doesn't consider different rheologies. So we have tried to take 3 different rheologies. We want to make a generalized model. So that was actually one of the requirement of the ISRO, wherein because we have different rheologies in different parts. So we want to generalize models they want to develop. So we consider 3 different rheologies and using this, whatever the available resolution maps, satellite maps. So these were the different case studies. So you can see here some of the Google Earth images of different debris slides. So this one you can see a remarkable rise in the number of debris flows was observed since 2018 in this region because of very high intensity rainfalls. And as I said, this study we have done geotechnical investigation, runout modeling, and also the calibration of the frictional parameters for long runout debris slides because they were almost 3 to 3.5 kilometers. And the detailed investigation, the back analysis for each event was substantial in calibrating the flow in these particular things. And these parameters were used for predicting the flow paths for possible debris flows and also for the quantitative risk assessment in the future. So I'll just take one of the sites. So this is a Kuchimerla site landslide debris slide that happened. You can see here in the figure, the track was almost like 3.3 kilometers. It was like into 4 different tracks it followed. So what we did is this is some of the field photographs where we have done the investigations, both geotechnical and geophysical. This is the data. This is you can see here there's a fine sand, fine to medium sand, and then there is a silty sand with gravel, and then the hard rock. So a dynamic numerical model like ramps. First, we started using the commercial tool ramps 2D. Was used for the back analysis of this debris flow using the shape information based upon the Google Earth, and then the predicted shape was compared with the actual one using 2 different approaches. In the first approach, the predicted width at 13 different cross sections, as you see here, different cross sections in the left side elevation profiles. So were compared with the actual width of the flow, so that we can find the best predicted shape. And for precise calibration using the statistical comparison, and we also use the image processing tool to compare the structural similarity of these simulated results with the actual original shape of the debris that flow slide that happened. This is the novel approach which can be used for calibration of the frictional parameters using the shape information. And this has been published in Landslides. Interested can go and check. In the example of this one, Kuchimarla, what we have done is that the dry Coulomb friction coefficient was calibrated, and also the turbulent friction coefficient was also using the Volney's rheology equations, and the shape whatever we predicted by the model had a similarity index almost like 0.6%, so which was like very good, and the results were found to be in accordance with the actual field and the geotechnical observations which we had done during the field visit. And then the results were used to predict the shape of the possible debris flow in the study area. So which we have done it. You can see here whatever the different parameters or the quantitative parameters which we compared it through RAMs. And then similarly we have taken other debris slides also, like Kutimala slide, and here also we have done. Then this is a Maniakunnu. So just show what are the different types of debris slides, and how the back analysis has been done. These are the examples of the simulation results which have been calibrated for the frictional parameters. So, and then we started looking at the comparison. So Pachar Kodli. So this is another debris slide. And Petimudi actually there's a lot of the risk associated with this particular debris slide was higher when compared to the other slides, because it was very near to the town, small village of the town. So the risk associated, what we observed, was very high. And so this is some of the investigation details on the photographs. Then this is the quantitative comparison of the results, whatever we observed. Then after this, we want to quantify the similarities, as I said, like, using different techniques. So this is the topographical parameters that what we consider for similarity analysis. So which we have done it. Then we try to look at this similarity quantification of the similarity index with the different parameters. So we have taken for all the sites, site 1 and 2, 3, 4. So then, like, we try to plot this similarities as well. And then after this, our actual work was like, there are some equations on the left side. I can share the slides because work has been already published, and this particular code was also patented. So this is actually what we have done is, like, we developed a two-dimensional debris flow model which assumes the flow material to be a single phase and also the homogeneous. So following the classical approach of the debris flow modeling, so the flow here is modeled, as I said, like two-dimensional continuum using depth integrated shallow water equations. So this is actually how we made it, and we have like very user-friendly GUI also has been developed for this particular DFS code. And this particular code has been validated taking the examples not only from the Western Ghats, we also taken examples from China and Italy as well. So I just put one slide which is there in China. So this is actually Indo Gully in a Xinjiang province of China. So this is on the right bank of a particular river like Baisha or something, and this general flow of the direction is from the northeast to the southwest. So, and here what happened during the Wenchuan earthquake, which caused 5 collapses and 1 shallow landslide in this particular debris flow area. It also had the circulation area was also been observed, which provided a very rich source of debris flows. So this particular slide has, data was been there, and I should acknowledge the data which has been shared by Dr. Tian from the Institute of Mountain Hazards from China. So this crustal activity in this gully is very strong because it's in the very active seismic area with faults which are developing from the north to south. So we have taken this particular thing to validate our code, and then finally we validated the tool. So there was like the catchment area is also around 1.1 square kilometers, and what we observed is like the blocking of rivers due to debris flows are increasing, and such debris lead to a lot of cascading effects, which is a huge losses were observed. So, and the average rainfall in this entire basin was also around something around 1700 mm, and the main gully is around 2.5 kilometers long. So we use this particular data for validation of our code. So these were some of the results from our validation for this particular gully or the debris slide. For the process of the calibration, we use 20 different sections, as you see here. So different 20 sections have been used along the flow path. So these cross-sectional areas of the debris flow path at each section was calculated using the pre and the post DEM data. And during the flow, we also see that there is a the cells and can be subjected to a lot of erosion and deposition. Actually, but every pixel, the rate of erosion and the rate of deposition can be calculated using the tool. This is a very unique available observation what we found in the cell elevation, and therefore erosion or deposition can be associated with particular cell or the pixel in that particular area. So what we did is like cross-sectional area of around 20 different sections were then compared with the observed values so that we can understand the effect of varying frictional parameters. So that's all. Thank you so much. Hello.
Thank you, Professor Nilima. Very research-oriented and very useful lecture you have delivered. And prediction is more important. If we are able to predict, then we can take precautionary measure, or we can just tolerate the incident. Anything is going to happen. So now the time is for the question answer. And the chat box, I'm saying 3 questions. So should I take it from the chat box or call the participants to ask the question? So, Dhruva Podial, are you there?
I can see one question.
Yes, sir, I am.
Yeah, can you ask your question? First question to Professor Atula.
Yeah, but we have a lot of these soil nailing and rock anchoring activities here in Nepal because of very steep slopes along the road corridors. Am I audible?
Yeah, you are audible.
Yeah. Okay. So it is not possible to make an experimentation of each and every anchors so that it has a sufficient pull-out strength. Would you please share some of the very innovative ways so that the pull-out strength is assured, or if not, what can be done to enhance the effectiveness of such anchors?
We generally estimate the pull-out resistance with shear strength parameters, taking saturated shear strength parameters, and then we do certain number of pull-out tests on the in the site. We do certain number of pull-out tests, getting completely pulled out, getting the strength determined, and also sometimes we test the actual nails for pull-out resistance. In that case, we can't get the complete pull-out. So we conduct the confirmation of pull-out strength on these modes. So generally, we have noticed the pull-out strength that we observe in the field is much greater than what we have generally assumed in the designs. Sometimes the unsaturated nature of the soil is also sort of responsible for that, because we in the designs we assume the pull-out strength based on the saturated shear strength parameters.
So, in locations like in Sri Lanka, where it is not very difficult to make a test, every now and then go there and observe the readings. How you can manage such thing in very steep slopes? If you have seen some of the slopes of Nepal, then do you
now
have some unique measures or some?
Now, in steep sort of very slopes of greater height in Sri Lanka, we have used kinds of scaffoldings to reach the height, and in some cases, we have used cranes. From a crane, so in the crane bucket, that we have done the drilling from the crane bucket, lifting the drilling machine to the required elevation. So it is not very stable, but in some situations we have done very sort of high elaborate scaffolding to reach the heights.
Then the cost implication of that?
Yes, in that case there is a significant cost increase. Yes.
Thank you very much, sir.
Why you are having one question with the Professor Nilima Satyam also, you can ask your question.
In these empirical models, especially for the areas where studies were performed, are there some precautionary sort of thing so that these models can be replicated to areas where studies are yet to be done or are not done?
Okay.
And also, in addition, can these prediction models be amalgamated with GIS maps so that every one can learn out of it where is the risk hazards are?
Okay. Sir, I'll start with your first question. The first question was like, these empirical models. So actually all are not empirical. These forecasting models, I started with all the empirical models and probabilistic models are there and highly advanced algorithmic models are there. So wherein like, it is all based upon the availability of the data. So if you don't have it, so only have like, point data from the landslide inventory and the rainfall data is only available, then, you have to go with the ID thresholds, which are very deterministic and may have several false alarms. But, what we tried is like, because we were started this as a first study in 2016 for the first case study, which I explained as the Kalimpong here. So what we try to do is like, we applied all the models, okay, forecasting models, all are not empirical. So this is the first thing I would like to mention you. So all the models on the particular study area to see that which is more, which is having less false alarms or the missed alarms. So that was actually the first part of the question. So then like, another very observation what we made is like, whatever the model we had, okay, 67% of efficiency in Kalimpong was giving very high efficiency in Western Ghats. Okay, so it is a site specific study, this I want to mention, and completely depends upon the data. So that is the first question. So the second question what you are asking is like about the what was the second question, sir?
Using GIS.
Yeah, exactly. Yes, we can make it. If you see my second part, basically for the landslide, dynamic landslide susceptibility map, which we made it at the panchayat level or the ward level. So that was actually based on a GIS map. So the base is like, GIS map. So we always can integrate that with the GIS maps, and yes, it can be possible.
Thank you very much.
And I have one more question. What is the life of sensor? Actually, it needs maintenance, annual maintenance. So every year before monsoon, so we have to there and we do some maintenance by changing the batteries and other things. So if you can do that, the sensors, of course, if it fail, we'll lose that. And otherwise, we use the sensor for 5 years. After that also it may be working, but since the project was closed off, so we have retried because our goal is not to monitor. We have monitored only small part of the larger area. So because monitoring is very expensive and it is practically not easy also. So so that's why we have done that for 5 years. But since the last 5 years we didn't had any problem. And in another site also, if you can maintain it well for the last 2 years in Joshimath, we have been monitoring. So yes, the sensors are robust.
Next question is from Rajul Dwivedi.
नहीं अभी आंसर किया मैं राजुल.
Yeah.
Rajul, you are okay, right?
Rajul?
Yes, ma'am. Yes, ma'am. Good evening, sir.
Collapsing a large group of boulders are common during landslide. Therefore, there may be significant effects due to presence of boulders or highly fractured rock inside the slope, especially if those are arranged. Okay. Okay. Yeah, that is possible, especially for the mixed kind of slopes. We also have encountered this one in Uttarakhand. Okay, so this is like, we had a huge boulders and also soil. It's a mixed kind of material. But whatever the two case studies that I showed, they are basically soil slopes. And maybe it can also be both the percentages. Okay. Okay, so Sir Atula sir can also add to that particular question from Sushita. Yeah. If there are any questions, yeah, please. Hello?
Yeah, Sushita? I think she has left.
Can I put one question? I'm Dr. Dhawan from Delhi.
I'm Susita. So
Yeah,
do
Susita.
I need to raise the question?
Madam?
Do
Yeah,
I
Susita, sir.
Just one small question. The probabilistic models that you have used in your analysis, what are the parameters that you have been able to? I just want
Yeah, for control probability, we use the rainfall event details, duration, intensity, and incident rainfall.
Mm-hmm. And what is this VES profile? VES profile, what is that?
Okay, that is a geophysical test which we have done, and some parts in this debris sites, ERT, resistivity, electrical resistivity, vertical electrical resistivity test.
Right. Thank you.
Sure, sir. Thank you.
Susita, you can ask.
Yes. This question is about if the rock boulders are available inside the rock slopes, especially if they are arranged in an unstable manner inside the slopes, which are not visible. So actually, there may be some moments inside the soil of the boulders in the presence of water pressure, poor water pressure inside, due to the difference between the boulders and the soil, there may be inside the relative moment. Is there any method to consider the effect of the boulders inside the slope, in the slope stability analysis, or in the finite analysis, whatever the analysis?
Yeah, there is no sort of direct way of incorporating the effect of these boulders on the general stability of the slope. So boulders are in a matrix of soil. So what matters for the global stability is the strength of the soil. So we do the stability analysis based on the strength parameters of the soil. But when we do the excavations, if you find there are boulders in an unstable state, we try to sort of remove them physically, or do some kind of stabilization, grouting, not exactly grouting this by building up around the boulder to make sure that it will not topple. So there's a two way. Sometimes we do controlled cutting of the boulder, remove part of the boulder to make sure that it is stable, right? Sometimes we purposefully remove it down. right? So those are the ways that we normally handle the boulders present in the cut slope.
Yeah, actually, that is, if it is visible, that is, if that is in the cut plane, actually we can remove. If it is inside the soil wedge, which is moving in the like, so if it is not visible, if it is inside that one, actually, is there any prediction method?
No, there is no prediction method for its behavior, but generally, if it is inside, well embedded in a matrix of soil, there is we don't take it. We are not concerned about its stability. Generally, what we have found is that's not a big issue if it is well embedded in the soil. But with this contrasting permeabilities, we have to take various precautions about improvement of surface drainage. But other than that, that is not a big concern.
Due to the relative movement between due to the low shear strength within the soil in the presence of
no. If the boulder is completely embedded in the matrix of soil, so there is no basic risk involved.
Thank you.
Thank you. I think we should go for the next question. There is no another question, only compliments and thanks to both the authors, both the speakers. And I would specifically like to read if Bhandari sir permits his comments on this webinar.
Thank you. I heard with rapt attention both the noted speakers, and I'd like to congratulate both the presidents for initiating this event. Now, when you have given this opportunity, I have one suggestion and one question. Both the countries have a history of working in this area. I'm familiar with both of these countries and in as much detail in Sri Lanka as here. And my suggestion is that our prime focus, whereas intellectual excitement and pursuits are most welcome, and we should reach the highest ladder of R&D, our main focus should be on saving lives. And therefore, in 3 or 4 decades of my experience, I've come to the conclusion in both the countries that we have to now talk about managed, credited, large-scale maps, and stop talking about small-scale maps. We have done enough of these. They are for planners and all that at large, and they are not going to help. So I would like to see more and more of large-scale, credible maps to come. Second is that we have talked enough about susceptibility maps. If we are really serious about saving lives, then we have to talk about credible hazard maps. And third is that when we talk in terms of early warning, if we are serious about saving lives, then we have to talk about known actual landslides which we have mapped umpteen number of times. Every year, those spots create problem, kill people. So I would like to see more attention paid to those cases. Now, coming to Sri Lanka, I would say Atula told about Watavala, that is the first case where directional drilling was used in Sri Lanka. But I would say that was the first example in the world. I actually want to tell you to this August gathering that we talk about rainfall. Rainfall is just one of the many factors, multiple factors which interplay on a geological time scale. So in some cases, it may be a dominating factor which attracts attention, but all the same, other factors are no less important. So in that case, what we have to do is to showcase examples, and Watavala is the best example. I would suggest both the societies to take a trip out to Watavala And I would actually be able to provide a note on this, an exhaustive note on this, where Sri Lanka should be proud of the fact that at the time when every global technology agency was putting forward solutions which were technology driven, in this case also is technology driven, but with due respect to geotechnical engineering. So therefore, drainage and drainage alone was the answer to this problem. High rainfall area, every year there was a problem. There were discrete boundary shears which are ignored in the area. And then when directional drilling was done to have the deep drainage, it became the first example where a major 100-year-old landslide was brought to rest without using a single retaining wall, anchor, or even the membranes and textiles and so on. So we can create these examples if we concentrate on major problems and then use our instrumentation. Now, my question is about the credibility of instrumentation, because I have considerable experience on this starting from 1967, when I used this transpressurized piezometers for measurement of pore pressures in mudslides of UK. And I find that one of the great compromise that we make is to rely on the instruments if they are buried for a long time. Their calibration is a big problem. And therefore, one is, where do we place them? How much we place them? How do we ensure their credibility? How we integrate the data? So my question is that first, we should, when we say rain-induced landslide, we are primarily giving less weightage to other prominent factors. We should be conscious of this fact. Otherwise, they are only rain-triggered landslides. Bishop used to call this last straw that breaks the camel's back. So this is one question that we have to be very careful in use of terminology, whether it's induced or rain-triggered. We simultaneously and interchangeably use these factors, which is not very good. Second is that when we have landslides, actual landslides, the measurements over the landslide in the crown region, in the middle of the landslide, in the toe region, you will get enormous volume of data on a long time scale. How do you make sense out of that data? How do you integrate that data to come to a conclusion is also something which is a debatable issue. I don't want to raise these issues here, but since you have given me the opportunity, these two things are bugging me, is the credibility of all that we do. It may be very good from the current state of the art, but the real test of success would lie in saving the lives. So I recommend that both the countries should actually share experiences on those case records, like Watavala. Surely Watavala is one where I can provide a lot of inputs, which will be of high educational value to both the countries. And that would stop the abuse of technology. You see, now there is a brutal force of technology to control landslides, which is actually putting geotechnical engineering on the back burner. I mean, you show an expert the landslide and he will try to fix it with technology. My suggestion is, let us respect our geotechnical knowledge and bring out technological solutions which will save lives. So with these things, I suggest both the societies that please include this in the bilateral cooperation, government to government cooperation, and try to enlarge the scope of it beyond seminars. I think what we should do is the joint initiatives in solving problems, visiting the places where best examples have been created, and even having joint discussions on roundtable on specific issues. I mean, too many issues are there in a lecture of 45 minutes, and you can't just do justice with it. So we have to have detailed discussions, and it should become a regular feature. Thank you, Dr. Singh, for this opportunity.
Thank you, sir.
My very sincere thanks to both the speakers and all those who have been present all through. I mean, I've seen after 3 hours also, I find something like 45 participants are still on. So it's a credit to it. Thank you. Congratulations.
Thank you. Thank you, sir. Now it gives me an immense pleasure to invite Dr. Anil Joseph to speak about Geotech Asia 2025.
Yeah, good evening once again. And thank you very much for both the speakers and both the societies for doing a great job. And say a dissemination of knowledge was happened in this webinar. But exactly as Bandari sir has pointed out, we need to take it further between the two countries, and end of the day, what happens in field and to save a life is a big achievement that can be achieved if the technology of prediction and protection, along with the support of both the societies together and actual action in the ground can be brought in. That should be our goal. And Bandari sir, we will definitely try to achieve that, and we'll take all our efforts to reach that. And Sagabandhu sir, both of us, let us together try to work out a solution in similar way, and we need your guidance and support also. So together with the experts, we will try to make it into a reality in the field, and that is a great achievement we can do for the society. Now, as the time is running out, let me take the pleasure of sharing with you a dream which is going to come true soon. And thanks to all the team here. Can you see my screen?
Yes, sir.
Yeah. Yeah. So the opportunity for is to welcome all of you for the first Geotech Asia 2025. Again, thanks to Sagabandhu Sahab and Mandeep for being part of with India to make it happen. So this is going to happen in Goa in 7th to 10th October 2025. So I request all of you to join us in Goa during those days. And it is in collaboration with IGS, in collaboration with IIT Bombay, is the joint host of the event. And this is something about IGS which I don't want to repeat, but we can see that we are working on quite a lot. And also, Bandari sir, we are trying to get the ISL 2028 to our part, and myself, Neelima and Samadhya sir are traveling to France, Chemberi for the process this time. This event is, this is the dates. Please note the dates. And I request all people to send papers for the conference, and let's have a great initiative. These are the team members, the National Advisory Committee, the team who is coordinating that. And these are the conference sub-themes which we have. And these are the rates. We are coming with a special package for the members of the Association of South Asia Geotechnical Society, so that we can have a special discounted rate for that. And thanks to Ashish and Dasaka Burti, who is working on in that and will be coming with that. And with a small video, I would like to end. And it's quite late, I know, but let's see this video and request all of you to be part of this first Geotech Asia in Goa in 2025, 7th to 10th October. So once again, I take this opportunity to welcome all of you to India for first Geotech Asia 7th to 10th October 2025. And thank you, EPSync, for giving me the opportunity to welcome all the delegates to India.
Thank you, Dr. Anil Joseph. And now I would invite Srilal Sabandhu sir to please give your concluding remark and vote of thanks to all the attendees.
Yeah, thank you, Dr. Singh. Dr. Anil Joseph, the President of the Indian Geotechnical Society, Dr. Mandip Subedi, President of the Nepal Geotechnical Society, distinguished guests at national and international levels, past presidents and members of the executive committees of both Sri Lankan and Indian Geotechnical Society, members of the organizing committee, members of both Sri Lankan and Indian societies, and ladies and gentlemen. I deem it is a privilege to have been asked to extend a vote of thanks on this first webinar organized by two societies. This day will be remembered as a milestone in the cooperation between Sri Lankan Geotechnical Society and Indian Geotechnical Society. The very presence of Mr. Kumar Bandari and Professor Madhavi, Dr. Anil Joseph, Dr. Mandip Subedi, in spite of their extreme busy schedule, is a reflection of the importance of that is attached to the development of geotechnical field in this region. We are all inspired by your gracious presence. I would like to take this opportunity to express our hearty thanks to Dr. A.P. Singh, the Honorary Secretary of Indian Geotechnical Society, for his commitment not only for this event, but also for the commitment to improve the relationship between two societies. We are extremely thankful to Professor Atula Kulatilaka, Emeritus Professor at the University of Moratuwa, Sri Lanka, and Professor Nilamya Satyam, the professor at IIT Indo, India, for their very informative presentations. I also extend my thanks to Professor Udeni Navagamua, Honorary Secretary of Sri Lankan Geotechnical Society, and other EXCO members for their continuous support in organization of this event. Similarly, I extend my thanks to officials of Indian Geotechnical Society and the organization committee of this event for their tireless work to materialize this webinar. Also, I would like to appreciate all the participants in this event, because without you, this event will not be very much valuable. An event of this dimension cannot happen overnight. The wheels start rolling months in advance. It requires meticulous planning and execution and eye for details. I and Dr. Anil Joseph have been fortunate enough to be backed by a team of very motivated and dedicated colleagues who knew their job and are result-oriented. I cannot thank everyone enough for the involvement they have shown and the willingness they have expressed to take on the completion of tasks beyond their comfort zone. With that, I will thank you, everybody, and we will meet soon with similar event. Thank you.
Thank you.
Thank you. Thank you, sir.
Thank you all.
Thank you, Dr. Joseph.
Thank you, Mandip.
Mention, can I do? There is a recent call between Indo-Sri Lankan for research funding from Government of India. So if anybody is interested, so I think they can cooperate even in that. So there's a recent call. I can share it with the President of Sri Lankan Geotechnical Society.
Yeah, you are welcome, madam. Actually, I was told during the rookie conference that there is a fund available and it is not utilized. It is underutilized basically. And if we can do something, it can be used to train our postgraduate students, and also it can be used for the common research interested for both parties. I think if somebody can initiate, because the fund is from your side, if you can initiate from your side, it will be very useful for all the people, all two countries.
This is actually the deadline is next month 30th, I guess. So I think that call has, the geohazards is one of the key areas where we can apply for funding. I just remembered that, so just mentioning.
Yeah, if you can communicate with us, we will try to do something.
Send it to our IGS.
Yeah.
Thank you so much.
Okay, thank you,
Thanks
ma'am.
to everyone for giving me this opportunity, especially IGS, our president who has taken a lot of efforts. So thank you so much to both president and our honorary secretary, and also our counterparts, Lankan Geotechnical Society. Thank you.
Sure. Thank you all for joining today's webinar. And if all permit, can we just close the session?
Yeah, and
Yes,
also
yes,
a
thank you.
reminder for Geomandu in November
Yeah.
29th in Kathmandu, where we are all meeting. So please remember those days also. We all will be there at Mandeep, and we assure that we all will be there to support. And thank you for all the efforts you are taking.
Thank you.
Mandeep?
Thank you.
Thank you, Anil sir. Thank you, everything, sir.
Yeah.
Thank you. Thank you, Dr. Bandari, for your comments. Thank you.
Thank you. Thank you.
Right.